Ohm's law. How do we actually use it? Hello, lovely humans. I'm Jen Foxbot, and I'm very excited to finally be getting to a topic that's been on my list for a very long time. How to put Ohm's law into practice. Ohm's law is a really helpful and fundamental mathematical equation, but it's very simple. So if you're like, don't worry. It's very useful for electronics. If you ever build a circuit, or if you're curious about electronics and want to build a circuit and you're like, what is going on here? Or how do I make the right choices for the parts in my circuit? Ohm's law is going to be your best buddy. But it can be really tricky, given how seemingly simple it is, to actually apply it in practice. And as somebody who learned the theory in the classroom and they showed examples for really simple circuits, and then you go home and you're like, yep, that was me. We'll break it down so that you can actually understand what's going on and apply it to your own projects. All right, to do that, we're going to go and actually look at the circuit, and then we can write the equations and write some things down. So we're going to have to flip the camera view. So bear with me while we do that. All right, here we are. Okay, so if it makes you feel any better, this is the fourth take that I'm doing because Ohm's law truly is complicated. But the hilarious thing is that it is a ridiculously simple equation, seemingly simple. So Ohm's law tells us that voltage equals current times resistance. Oh, but my dear friend, you laugh. You're like, I got this, no problem. And me here on my fourth take, because even applying Ohm's law to a seemingly simple circuit is hilariously complicated, says, wait, don't get ahead of ourselves, because there is a lot of information packed in these three little symbols. Well, voltage is weird in itself. So voltage has to be measured between two components, or between 2 points. So it's kind of like distance, where you would say, what is the distance to the library? Not like, what is the distance? And we're like, well, what is the distance between what and what? So voltage needs to have a starting point and an ending point. You have to measure the voltage, say, across the batteries, or across the light, but you can't measure the voltage, just in a wire. I guess you could measure the voltage across a wire, but it must be between 2 points. So that is a little tricky, and we'll look at that in more detail. We'll learn how to apply that. And then the current is the current running through, through the part, or through the part of the circuit, and then the resistance of that part, or how much that particular component resists the flow of electricity. So voltage across, across part. Sorry for my handwriting, like I can't even read that. A current through the part and resistance of that part. Okay, so let's analyze our simple circuit with Ohm's law. I have valuable real estate in the center, so we'll move Ohm's law up to the corner for easy reference. Okay, so anytime I build circuits on a breadboard and I'm dealing with Ohm's law, I like to draw a picture, because like pictures are way easier to work with, because I can annotate them, meaning I can draw things on them. So sometimes if you're new to circuits and you're like, I don't know how to draw a picture of a circuit, just draw pictures. So like really, like sometimes I just draw, I'm like, look, there's my LED and there's my resistor. But if you want to, sometimes it's actually easier to draw the circuit diagram. So circuit diagrams use symbols. That's kind of funny. Use symbols to represent electronic components. A long line and a short line represents a battery. An LED is a triangle, pointing in the direction of the current flow with an arrow coming out, because it means it's a light emitting diode. Cute. And then a resistor is a squiggly line, which I really like. Okay. Oh my gosh, that is not a straight line. Oh, rude. So rude, I know. How dare I not draw a straight line? Okay, so we have our battery, our LED, and our resistor. We're going to label them because it makes it easier. So I'm going to label this R1, L1, and I don't know, BAT, or battery. Okay, so the first thing to note is that current flows out of the positive side of the battery, is defined to flow out of the positive side of the battery. So then it flows to our LED, and then it flows through our resistor, and then it comes back to the battery. So there's only one path for the current to flow. So the total current is also the same as the current that goes through our LED and the current that goes through our resistor. So in other words, the total current of our circuit equals the current through our light, and it equals the current through our resistor. So that's pretty cool because right off the bat, we know something about our circuit. The reason why this is the case, well, I mean, you can kind of visualize it here, right? Charges that leave the battery have to go somewhere. They can't just disappear. Whole thing of, mass charge, energy conservation, that type of thing. What you start with is what you need to end with. It might go in funny places, but you have to, you can track it down, basically. So this also put into words and not mathy language, or put into, I'll say English words, is that current is the same in series. And series just means things are connected head to head or tail to tail. There's one loop for our circuit. Okay, so now we can ask, well, what is the total current? The total current is going to be given by Ohm's law. So this is where we have to be really careful when we apply Ohm's law. And this is why I like these little subscripts on all of these different symbols. So I write total on each of these to keep track of what I am calculating. Because with Ohm's law, as I mentioned, specific voltage for each of these components, current for each of these components, resistance for each of these components, use subscripts. They will save you. Okay, so I can calculate the total current by dividing by resistance. So I get V total divided by R total. Okay, so now we're like, what is V total? Well, hey, look at that. We have AA batteries. And a single AA battery, or VBAT, is 1.5 volts. I have two of these, so V total, and as an aside, I have two of them in parallel. We may get to that, but in parallel they add, 1 volts plus 1.5, oh my goodness, plus 1 equals 3 volts. Okay, so V total is 3 volts. We got there, kind of messy. Okay, but what is R total? Well, we have a resistor, and I know the value of the resistors because I pulled it from this package, which says 100, and the thing that they left off, because when you're looking at resistors, you're like, ah, yes, it's in units of ohms. But we're not going to leave the units off because we are good scientists and engineers, and math people and lay people and people that do math with units, because we're talking about the real world. Okay, so 100 ohms for our resistor. But our LED also has some resistance. So I'm going to actually label this resistance of the resistor, so RR. And then our LED, I had to look this up because it changes depending on the voltage and current in your circuit. So that's fun. This is why it's a seemingly simple circuit, right? Okay, but now that we have, bumped it. One more thing. So our total, we're going to add these in series. Resistors add in series. We'll add that as a side note down here. Actually up here. Okay. So our total equals R1 plus R2 plus ... plus however many resistors you have for series. So like I said, Ohm's law, deceptively simple, because there's all these other equations hiding behind it that we need to know. But that's okay, because we're smart and we can handle it. We just take it one step at a time and use subscripts. Okay, so 100 plus 250 is 350 ohms. Alrighty then. Okay, so V total is 3 volts divided by 350 ohms, and this is something like 0.008, or about 8 milliamps. Okay, hold on, I'm gonna double check that. Okay, JK, it's actually 0.0085. So we're gonna round that up to 9 milliamps. Okay, so this is I total. And I'm gonna write that under this circuit. So we save that, equals 9 milliamps. Okay, so that means, oops, I keep bumping the little, keep bumping the camera. Sorry about that. It's like you're here with me. Huh. Okay, so that means that the current flowing through our light is 9 milliamps, and the current flowing through our resistor is also 9 milliamps. So we have actually gone through the puzzle and started to solve for some of these mystery numbers in our circuit. So we now know the current and voltage flowing through, we know the current and resistance of each of our light and our resistor. So that means we can calculate the voltage across them. Let's start with the resistor, because that's easier math. Okay, so voltage of the resistor equals current through the resistor times the resistance of the resistor. And we know that it's the same in series, so this is going to be 9 milliamps times 100 ohms, which is going to be, this is 0.009. So this is going to be 0.9 volts. Okay, and then voltage of our LED equals the current through the LED, which is just the total current, times the resistance of the LED, and that's going to be 9 milliamps times 250 ohms equals about 2.25 volts. Okay, so that's pretty interesting, right? So even though the current, the charge flowing through our circuit is the same, the voltage across the components in parallel is different. So let's add a little bit of a caveat. It's the same in series, but voltage is different. Okay, so that's pretty cool. And you know what we can do now, when I get my my eraser rag out of the way? We can use our handy dandy multimeter to check our work. Huzzah! Okay, so, okay, I'm gonna put it in a spot where hopefully you can read it, and I make it a little bit more legible. All right, so what is the voltage across the resistor? Oh, look at that, 1 volt. What's the voltage across the LED? Oh, 2 volts. All right, hot damn. Okay, you're like, it was a little bit different. You know what? Welcome to the real world, honey bear. Yes, it was a little bit different. And the reason is because I am estimating. I keep running off. I'm estimating the resistance of the LED because LEDs do not have a linear resistance, which means the resistance changes depending on the voltage and the current. And so I picked a value that was close enough. But you get the picture. The key here is that we're in the ballpark. Yes, we are in the ballpark. Certainly. We're playing the same game, which is also really important. And it is really, really cool that we can use theory to kind of get some understanding about how the real world is going to work. So, you know, if we were doing this for realsies and like a real science experiment or a really sensitive circuit, we would just need to be more accurate with the resistance of the LED, and then we would get closer to the voltages. But for hobbyist stuff and for just like trying to understand what is going on in this circuit that we can't see, but we can use math to better understand, well, math and it's amazing. And the key here too that I wanted to highlight is that while the current is the same, the voltage across these components, so V resistance, the voltage across the resistor, and the voltage across the LED, V LED, this is why I drew it too small, sorry about that. These are different. These two values are different. And that's really critical because we need to know that the voltage changes in a series circuit. Okay, so that was a simple circuit for applying Ohm's law. And now we can understand why Ohm's law is a sneaky little tricksy shark shenanigans. Sharks aren't tricksy, but it kind of is alliteration. So sneaky little squid. I'm running out of analogies here. Okay, this is my fourth take. I finally got it right. The resistance of the LED was tripping me up. Okay, so it's hard, like legitimately. Ohm's law, applying Ohm's law is hard because there are so many different kind of variables and things that you have to keep in mind. But at the heart, it is really, really helpful to understand, like, if something weird in your circuit is happening and you're like, I don't get it, you can use Ohm's law to figure that out. Or if you need to figure out, like, well, what is the smallest value of a resistor? What's the largest value of a resistor that I can use with my light? You can go and look up the data sheet. Data sheets are your friend. A data sheet for a LED, and you can say, okay, well, I need to make sure that it gets, it doesn't get above this current or this voltage. So you can figure out what resistor to use for your battery, or alternatively, you can also figure out what batteries are appropriate. So data sheets. Okay, that's truly applying Ohm's law in the real world means looking at data sheets. But once you don't have to read the whole thing, just look for what you need. Smiley face. Okay. Okay. All right. I think I'm going to leave it there because just doing Ohm's law for a series circuit with two components is pretty tricky. But please let me know if you would like, well, actually, okay, what I'm going to leave you with, okay. Let's say we have a parallel circuit. So, a parallel circuit means that you have two loops. Oh, that's a really bad resistor, even for me. Goodness. Okay. Okay. So you have your battery, you have light 1, you have R1, you have light 2, and R2. So in this case, you have two loops for the current to flow. So the current can leave the battery, flow through the light to the resistor, and then through this wire and back to the battery. So you have one set of charge pathways. The current can leave the battery, flow through this light, this resistor, then come down here, flow through that light, that resistor, and then go back up to the battery. So you kind of have like this path right here. So this is I2. So this is a little bit tricky, but one thing that I want to say is that never fear, because current has to be conserved. So the total current must equal I1 and I2. Yes. I guess I2 would be the total, because then you could also have this third loop, so I3. Or I could say this is I2 and this is I total. Sorry if that was confusing. The total current would be kind of like flowing all the way on the outside. So I total. All right, ignore this one. But you could have current that kind of just like flows through this loop right here. And so that would be I2. But it all must be conserved because you can't lose charges. They gotta be somewhere. The charges that leave the battery are going to come here. And you're like, but what about heat? You're like, yes, but generally speaking, we're not doing this in a science lab right now. We are doing this to understand it. So current must be conserved. We're not concerned about current charges leaving through heat, etc., etc. The vast majority of charges that leave the battery will come back to the battery. And then the one thing that I will say is that voltage is the same in parallel. So if we were to collapse these two parts of the circuit and you were to measure the voltage across them, it would be the same. And also remember that V total, and you're like, wait, what did you just say? So V total must equal the voltage across circuit 1 plus the voltage across circuit 2. So basically, you could like redraw this circuit as like just like 2 loops, and then you could say this is component 1 and this is component 2, and you could say the voltage across C1 is the same as the voltage across C2, where you combine the LED and R2, and then you can kind of separate them out and treat these two circuits separately. So you would find VC2 and then apply it to this one, and you'd find VC1 and apply it to this one, and then you can find the total voltage, because it should be the same. Okay, all right. That was a lot. I hope that that is helpful. Remember, number 1, draw a picture. Draw a picture. Label the picture. Number 2, use subscripts. It will save you. Number 3, take it one step at a time. One step at a time, okay? And just if you get stuck or confused, kind of another tip that can be helpful is to kind of like label out all of the things that you need to find, all of the information that you have, all the things that you need to find, and then use that to systematically go through and calculate the things that you need to find. Take it one step at a time. You can totally do this. And it is okay to draw and redraw your diagrams to make them messy. And if you have to turn them in to somebody else that needs to look at them, you can always redo them and make them, or like, you know, just take a new sheet of paper and make it clean and easy to read, and that will help your understanding as well. It really, really is a truly useful equation. I have definitely used it in a lot of my circuit projects where I was like, what is happening? What do I do? Or like, I don't want to explode this component. I need to figure out what battery to use and what resistance to use. And then that way you can protect your beloved microcontrollers and circuit components from your power supply. Good times. All right, my dear friends, please let me know if you have any questions or if you have any other topics in science, tech, engineering, and math that you're curious about, and let's get a tackling. I'll see you next time. Goodbye.